Good day all. My name is Oluwaseun Omoniyi. I am one of the authors of this work, and I am a PhD researcher at the Center for Ultrasonic Engineering, University of Strathclyde, Glasgow. My research interests include 3D printing technologies and the development and characterization of new materials. Thank you for listening. I am here today to present our work titled A Novel 3D Printed 03 Piezocomposite Material for Sensing Applications. The design and fabrication of composite materials enables the optimization of electrical, magnetic, and mechanical forces for sensing applications. The drive for the rapid development of piezoelectric composite materials is a must. This stems primarily from the need to combine desirable material properties to maximize the input and output response of electromechanical sensors. Piezocomposite materials consists of the combination of piezoactive materials such as ceramics and a passive material such as polymers or epoxy. The possibility of combining the most useful properties of these different materials to achieve the desired design goal when designing a sensor or transducer application. A piezoelectric composite exhibits the 03 pattern, where the piezoelectric ceramic particles are dispersed within a polymer matrix. In this pattern, the ceramic particles are not in contact with each other. Transducers for sonar applications have been fabricated using the 03 piezoelectric composites due to their ease of manufacture at large scale and inherent flexibility. Further application of these composites is its use as piezoelectric paints and for damping mechanical vibrations. Additive manufacturing or 3D printing. This is the construction of a three-dimensional object from a CAD model or a digital 3D model, usually achieved in a layered approach. Additive manufacturing of piezoelectric composites has the potential to open a pathway to low-cost fabrication, tailored products, and highly detailed, high-fidelity designs. However, printing of these composites and obtaining higher D33 coefficients by increasing the concentrations of the ceramic particles trades off the ease of processing the resins for increased functionality. A high particle concentration often leads to high viscosity and significantly inhibits the ability to form intricate geometries. The ability to fabricate these parts via photolithographic additive manufacturing processes relies on loading a UV curable base resin with piezoactive nanoparticles to produce a piezocomposite with the 03 connectivity pattern. Lead magnesium niobate, lead titanate, is a piezoelectric solid solution consisting of lead magnesium niobate and lead titanate. PMN-PT single crystals have been shown to exhibit ultra-high piezoelectric performance with piezoelectric constants D33 ranging between 700 and 2,800 picocoulombs per Newton. The PMN-PT powder used in this work has a yellowish-green appearance with a melting point of 1,264 to 1,320 and a density of between 8 and 8.2 grams per centimeter cube with a size of 5 microns. Gray resin is a proprietary and commercially available resin for high-resolution, rapid prototyping. Gray resin is a liquid photopolymer that will cure when exposed to ultraviolet light. When fully cured, the resin is flexible and smooth. Gray resin is cured by ultraviolet light with a maximum absorption within the range of 350 and 405 nanometers. This work is split into two parts. The first part involves spin coating and curing the sample under UV lamp, while the second part involves 3D printing a block using the same piezocomposites. Figure 1 shows the process of fabricating the piezocomposite material using the spin coating technique and also curing under the UV lamp. Step 1 is the material formulation. Here we mix 70% by weight PMN-PT and 30% by weight of gray resin together. Step 2 involves solution mixing. Here we use a planetary rotatory mixer set at 1200 RPM for 45 seconds, and the mixtures are also deformed for 15 seconds at 1200 RPM. This process ensures a homogeneous mix and also removes any air bubbles present in the mixture. The third step involves spin coating. Here, we put small samples on glass slides and place in the oscillar spin coater set at 2000 RPM for 10 seconds. And this gave a layer thickness, a sample with a layer thickness of 90 microns. The speed and time chosen here was by trial and error over a period of trials. Step 4 involves polymerization. The spin-coated samples are placed in a bag containing nitrogen gas before being placed under the UV lamp. This process enables quick polymerization. The samples were cured within 20 minutes, whereas if this method wasn't used, it took a longer period. 3D printing. Step 1 and step 2 of the 3D printing process has been outlined in the previous slide. Step 3, which is the 3D printing itself. Here, this is achieved using a commercially available 3D printer, Asiga Pico 2 HD. This process is shown in figure 2, which shows the schematic of the bottom-up digital light processing technique used in the 3D printer. The CAD model was first prepared using the 3D printer software, Asiga Composer. The printer projects images at 385 nanometers. The piezocomposite mixture was placed inside the build tray. The build process begins with the approximate positioning of the build tray 100 microns from the Teflon base, and overexposure of the resin to create a burning layer to ensure adhesion of the printed parts to the build block. The build progresses by raising the platform by the build layer thickness, repopulating the tray with the resin for subsequent layers. The print exposure time, burning time, and slice thickness resolution used for these prints are shown in the table. These were achieved through trial and errors of several prints obtained at different times. Once both samples were fully cured and printed, we polled each of the samples. These samples were polled by applying a constant high electric potential and high temperatures to the samples as shown below. Each sample was placed in silicone oil heated to a temperature of 120 degrees and a constant electric potential of 9 kilovolts applied for 3 hours. Most samples polled under a higher electric field were damaged due to the very high field applied. The figure 4 shows an example of the 3D printed sample. Figure 4a shows the card model used to print the sample, while figure B shows 2 sample blocks of the 3D printed sample. The samples were flexible and fully cured. Figure 5 shows a sample fabricated using the spin coater and cured under the UV lamp. The sample was very flexible and thin, and it also shows the conductive tapes and silver coated on the samples. Both samples are firmly glued on glass slides once polled and once the conductive tapes are applied. This was done before characterization using the LDV. Morphology. The microstructure of the 3D printed sample was examined using a scanning electron microscope at an accelerating voltage of 15 kilovolts. The distribution of the PMN-PT nanoparticles in the polymer matrix can be observed in figure 6. Figure 6a shows that the PMN-PT particles are well dispersed and distributed throughout the sample. However, it was observed that PMN-PT nanoparticle clusters were observed in different regions. Figure B takes a closer look at one of the clusters. Here, it is seen that the clusters are densely populated, and this reveals a non-0,3 connectivity pattern. So it was observed that the sample actually consisted of both 0,3 connectivity pattern and a non-0,3 connectivity pattern. Previous researchers have shown that the use of suffocants can greatly reduce clusters within the samples. These clusters could be as a result of the high PMN-PT nanoparticle ratio or the PMN-PT particle size of 5 microns used, or the solution mixing method used. Piezoelectric properties of the printed sample was investigated using a microscanning laser Doppler vibrometer. Here, a sinusoidal AC voltage of 10 volts peak to peak was applied across the axis of charging, and the resulting displacement along the polling axis was measured. Single point scans and full surface scans were performed. A single point scan and a frequency sweep stimulus was applied from 1 kilohertz to 20 kilohertz to obtain the resonant frequency. Here, the resonant frequency was obtained at 19.1 kilohertz. To obtain a more stable D33 coefficient, a full surface scan of 1000 scan points is then carried out and done below resonance. So here for this printed sample, we chose a frequency of 19 kilohertz and a frequency and a displacement, a D33 coefficient of 29 picometers per volt was obtained. A further measurement of the piezoelectric response was obtained using a quasi-static piezoelectric D33 meter. This was measured by applying a periodic force of 0.25 newtons to the sample. The table below shows the D33 coefficients obtained using each method. The D33 meter has been shown to provide a less desirable result, D33 result, because of the bending effect which occurs due to the pin electrode usually applied to the samples. Conclusively, a new piezoelectric composite material comprising PMN-PT nanoparticles and a photoactive polymer gray resin is presented. The process of 3D printing the composite and results obtained from the material characterization is also presented. The thin and flexible structure of the printed sample coupled with the piezoelectric properties and good print resolution at high loading of filler contents up to 70% weight shows that this material offers promise as a functional material which can be used in printing sensors and actuators. The SEM analysis of the composite material showed the 0-3 connectivity pattern of the composite and the agglomeration of PMN-PT nanoparticles at different sections within the bulk of the material. The results from the 3D LDV experiments showed a better method for measuring the piezoelectric constants of thin films rather than a D33 meter. The printed sample responded across all frequencies, ranging from 1 kHz to 20 kHz, with a resonant frequency at 19.1 kHz. The sample had an average D33 of 74 picometers per volts, which is higher than some reported 3D printable piezocomposite materials. The next step involved in this work is to enhance the D33 value of this new composite material. 3D print functional applications using this new material and simulate the acoustic and electromechanical properties of the material. Lastly, also characterize the material using FTIR, Raman, and XRD techniques. Thank you for listening. Questions can be directed to me via email at oluwaseun.omoniyi@strat.ac.uk. Thank you.